title is Soap Film Envision of Flapping Wing During Hovering. And please let the Chandrasekhar, you can present your thesis for about 30 minutes, and then is the all question and answer. Okay.
Okay, Professor.
Okay, please. Yeah.
Okay, so I'm starting.
Yeah.
Good afternoon.
Remember to do the recording. Recording.
Yes, Professor. The recording has been started.
Okay.
Okay. So good afternoon to one and all presented here today. My name is Chandu, doing my master's degree under the immense guidance of Professor Yang in Tamkang University in the Department of Mechanical and Electromechanical Engineering. I would like to extend my sincere thanks to all the committee members for making your valuable time for my oral defense within your busy schedule. I must also thank Professor Wu and Professor Hu for accepting my invitation for being my committee members in a very short period of time. And today I'm here to present my master thesis oral defense presentation. My research topic is soap film envision of flapping wing during hovering. So before starting to my presentation, I just want to show about the research background. I want to explain about a short note of our lab research background, which is mainly focusing on the long endurance of flights, the flapping mechanisms, the lift and thrust improvements, and CMOS MEMS flow sensors, and also the steady flow field using the soap film to visualize the unsteady flow. So now this is my outline of my today's presentation, where I'm going to start from the introduction to the research results and analysis, and I'm going to show my conclusion. So coming to the introduction, the methods of predicting the 3D flow field of a flapping wing motion using a soap film visualization. We have used 10 centimeter micro ornithopter or a flapping wing micro vehicle for this research. Flapping wing is penetrated through the soap film orthogonally, and its color field across the soap film is due to the flapping motion that has been observed through the high-speed camera. In this, we are going to find the relation between the color thickness field of the soap film and the corresponding 3D downwash induced by the wing tip vertices of the flapping wing is derived. We are using the standard thin film soap bubble colors and the wavelength charts so that the soap film thickness is computed. So now I'm going to explain about a brief history of the previous flow measurements. What are the techniques existing in the present day? So the first one I'm going to talk about the streamline direction, which is not only took off during the resonance of the preference. The first flow visualization of the turbulent flow has been recorded on the impressive drawings of Leonardo da Vinci from 1452 to 1915. Most of our breakthrough, however, only took place when the empirical data started to the methodological acquired to the proper instructions. So here you can able to see this is a kind of flow streamline visualization, and this is a kind of one of the technique. And the second technique we are going to use is like PIV techniques and standard smoke tracking techniques. So in fact, the qualitative information of the flow through the photographic has been obtained in the early 1917 by Nyers and Fizzards to inspection of the unsteady flow around a cylinder. They identified and tracked a particle images through 80 consecutive frames using the oldest tools known to man, their own eyes and their hands, where you can able to see it is like a 2D dimensional PTV measurements we have made using a 2D slice emulated by the thin laser sheets in a low density of seeding particles through the tracking each of them individually from several times. So moving on to one more new technology, which is very expensive, but which is rarely used in the coming technology, which is particle image velocimetry, like PIV, is a non-instinctive optical technique of a flow velocity measurement, which can capture the simultaneous information from about 103 to 105 flow points for the sufficient resolution of an yielding instantaneous flow vertices of the rate for the string. Yes. So now I'm just going to move at the purpose of this work. Why we have taken this work, especially on the soap film. So majority of the people are using only the particle image velocimetry, like which is PIV, with a high speed camera photography to measure the unsteady flow field, which is comparatively very expensive. So developing a new methods of soap film to observe and flapping flow field, and also the slow film visualization is similar to the smoke tracking methods. Now moving on to the scope and methodology of my entire research is, although we have been several important developments lately used in the soap film, the testing but the platform development of the first soap bubble seeds in the first measurement of the lift generation from high-speed camera setup with time response. The time response is very important when we are comparing the lift generation with respect to high-speed camera setup. Further advanced the reliability of soap film visualization system for hovering condition to identify the net forces acting on the flapping wing towards the point of research of flapping laboratory testings. Evaluating the experimentally the soap bubble tracking accuracy under the flow condition, the relevant previous streams and the starboard directions with the comparing data with the hovering concepts. So when we are demonstrating the feasibilities of integrating the soap bubble system with the different flapping mechanisms for the accurate of the aerodynamical force calculation using the Matlab image process technique. So now I'm just going to move on with the next slide, which is of soap bubble preparation. So how we started preparing the soap bubble for my experimental setup. Firstly, we had took some homemade soap bubble liquids which are with a different properties and made tests with a different ratios to find the long durability without the breaking point. So the first common ingredient we have used is ultra bubble water, and the second ingredient is the glycerin. Third one is about the dishwashing liquid. We have used all these liquids to make an common solutions with a different ratios where we can able to get the exact the breaking point of my bubble. So we have done some several kinds of tests which I'm going to display here. So I want to just show the testing of all the videos. So here you can able to see my test one is the solution ratio is 7:1:1, where we can only get approx like 2 minutes 45 seconds, and we changed with a different mixing ratios of the bubbles, and later on we have achieved like highest one. As we have done several testing ratios to find the maximum possibilities of the bubble duration and the mentioned test cases with a specific mixing ratio. At final mixing ratio of 2:4, the soap bubble lasted around like 6 minutes 14 seconds, which can able to do the flapping wing testing with a maximum number of flapping cycles before the bubble breaking. In the table, we have mentioned clearly of the mixing ratios of the solutions with the bubble breaking point with respect to the time. And also from these tests, we can able to easily say that the glycerin ratio makes the bubble to withstand the long time because its instantaneous properties, because the density of the glycerin is around like 1.26 grams per centimeter cube. As we have the good soap bubble breaking point, now I would like to continue with about FMWAV mechanism which has been fabricated based on our requirement. So moving on to the flapping wing mechanisms, we have selected the Evans mechanism for the soap bubble testing. Due to the longer wingspan of 20 centimeter, which has a high chance of breaking the soap bubble with the required flapping frequency. We have modified the wing design to 10 centimeter, which can reduce the bubble breaking chances of the flapping wing. So next, we have modified the 20 centimeter wingspan to 10 centimeter based on the experimental requirement. as we have used the PET material as for the wing, which can be cut using the graphite cutting machine, which is like XY cutting axis machine. So this image shows the wing placement of the Evans mechanism after the cutting the wing of 10 centimeter. So finally, the wing placement has been done, attached with the motors and wiring with the external power supply. Has now we have a good soap bubble breaking time, and as well as we have modified the flapping with the 10 centimeter wingspan, which can reduce the high chances of breaking the soap bubble with a lower frequency. So now we can able to move to the next experimental setup for testing the soap bubble, which can makes easy to record the high speed camera with a good color enhancement for a proper setting setup. So this is how I'm going to explain the step-by-step process of my experimental setup, how we have integrated my whole setup to get an accurate and good results of my video. So the first important thing is that the most important thing is the plastic frame, which can hold the soap bubble in the required shape. And later on, the next we have needed to set up a very good high density styrofoam boards, which can be act like an supportive walls, which can control the additional airflow around the soap bubble. And next we need to arrange all the light setup, which can plays a very important role in the experimental setup for the high speed camera video recording, which respectively to the frame rates. And next, plus the black color and the black screen can be makes the flapping flow patterns capture in the high speed camera video very accurate. So next we are moving when we can able to place our final MAV, which has been prepared before the experimental can be placed inside the soap bubble orthogonally based on the requirement. And next we can just make the bird fly and soap bubble based on the direction we required and capture the high speed camera video for the future post processing in the Matlab. So now I'm going to move with the different experimental setup where we have faced some kind of issues from we have generated from generation 1 to generation 4. So I'm going to explain one by one generation. The first generation we have used is like EPS box, which is like extending polystyrene box with of a front 45 degrees angle setup to capture the high speed camera videos which face the problem with the camera and the lighting reflection. Where here in the video, you can able to see, we have entered with a 45 degrees angle and the light angle, which will having a problem with the recording of high speed video. So we have been shifted to the second generation. We have implemented the boards in a triangular manner where the light direction will be changing with respect to the camera. So the setup of the modified second generation with the triangular setup box with the light facing towards the camera, which has been reduced most of the reflection problems while recording the high speed camera video for the starboard direction. So then we have moved on to the third generation modification of a semicircle shaped EPS sheets. Because of the distance between the camera and the soap bubble, we have close enough to capture a selective frame size. We need to have a selective frame size when we are recording with respect to the direction of the ornithopter. And finally, we have modified in the same concept of the fourth generation. We also modified with a vertical direction and hovering concepts of an high speed capturing video, where I can show all the testing videos of the fourth generation experimental setup output videos in the next coming slides. As I mentioned in the previous slide about the 4 different generations of my experimental setup modifications are only based on the 3 different kinds of my soap film interaction with my MAV, where you can able to see my y-axis and z-axis, which represents my plastic frame which is holding the soap bubble. H0 can be denoted as the thickness of my soap bubble, where you can able to see this is the starboard direction of my MAV, and this is the free stream direction of MAV, and this is a vertical direction. We have tested all three directions to find the downwash lift and V as the jet speed as a thrust. Based on these, we have derived the lift and thrust formulas, which I am going to laterly explain in the next slides. Moving on to the derivation part, aerodynamical force formulation across the SOF film. So we outlined the pros and cons of all these three cases of my SOF film, only adapted with two feasible SOF films to investigate the thrust and lift forces of my MAV. And the SOF film is apparently broken by the flapping wingtip, immediately not possible to realize herein. So where you can able, as I mentioned, this is my first case of by starboard direction, which I can able to derive. My first equation is like volume flow rate entering into the volume flow rate entering into the control volume equalized with the rate which the volume is changing with the control volume. So when I'm moving to the second equation, this equation can be simplified using the Taylor series expansion. So the mass conservation can be expressed by the Gauss theorem, where in the equation the mass conservation, the delta U can be expressed by the Gauss theorem. And equation 4, since the elemental volume of dV is h into dx by dy, and substituting delta U in equation 2 in the equation 3, so we can able to get the final equation of equation 4. The equation is represent the mass conservation relation with the time rate of the thickness. So the practical use of the equation 4 is we just block around the wing of the SOF film with the surface area integral with the time rate of the thickness according to the equation 4. Now moving to the second concept of the derivation is like SOF film normal to the starboard direction, and here in the figure you can able to see figure A. So assuming no velocity in the surface 2 and 3, but the average jet speed at the equal like point 1, it is the jet speed we have represented with V at surface, and the downwash speed is W at surface 4. The flow rate surface of 5 and 6 can be cancelled each other left hand side in the equation 4. So as we have mentioned, we have only one direction, so we have taken the equation 5, and in the equation 6, after replacing the integral terms with the summation, which leads to the defined discretized form of the integral with time rate of the thickness h across the SOF film area. Now we are going to derive the same equation with the y direction. The thrust is defined in the y direction, so we are using the momentum time rate. So we are replacing this with the momentum, so we can able to get the thrust. Similarly, the lift is defined to the momentum time rate along the z-axis, because this is represented in z-axis and this is our y-axis. And the y-axis we can able to consider this is a thrust force, and in the z direction we can consider that as a lift force. Now the similar equations transforming for the free stream direction. So now the bird is traveling in the free stream direction, where in case the surface 1, 2 and 3 has no velocity surface, and W, which is as the downwash, surface 4, the flow rate of the surface 5 and 6 can each other the left hand side from the equation 4. The equation 10 here, which is like downwash, after replacing the integral term with the summation, we need to replace this value with the summation to define the discretized form of integral to the thickness matrix, like thickness of H0, which can be represented the bubble thickness. So we can able to derive the same lift equation, and then the equation 12, which is like from the equation 11, as we already derived the lift, can be directly derived from the SOF film thickness matrix of Hij, and in the equation 10, the magnitude of the lift is to have the higher order, has to have the higher order of the SOF film thickness H, and can be regraded as a 3D lift to comparing the following. And we can able to find this V jet speed to the thrust, which is equation 13. Thus the thrust T in the equation 7 can be rewritten by interesting the jet speed v of the equation 12 of the downwash to the equation 10. Now this is the derivation part, which is like we will be going to use this derivation part later on the post-processing section. So now I'm going to show some of the videos of my high-speed cameras, as I mentioned in the different generations of the experimental setup slides. These are some of the high-speed camera videos with the starboard direction, free stream direction, vertical and hovering concepts. So this is the first video we have recorded using a high-speed camera, which is of 20 centimeter wingspan, where you can able to see there is an immediate break in the bubble because of due to the higher wingspan and also the sharp edges. So we have later on modified with a 10 centimeter wingspan, as you can able to see in the video. It is in the free stream direction with a 10 centimeter wingspan, and you can also able to see the flow patterns changing with respect to the flapping frequency. And now later on moving with the starboard direction, which right now the FW like MAV is moving in the starboard direction. Here also the same with the 10 centimeter wingspan we have used, and you can able to see the more vertices generated here. We can able to later on post process this in the image processing in Matlab. And most important point here is the ripples you can able to see when there is a video. So these ripples are the most important point we need to keep in notice, which will be useful in the next coming slides. And next, this is a one more video which is of vertical direction flow allows, I mean direction of my 10 centimeter wingspan, which is moving in the vertical. And finally, when we come, this is my final hovering test, which is holding in the same position with 0 meter per second of wind on it. So in the next, I also mentioned clearly which is of the upstroke and downstroke. So here in the image, you can able to clearly see it is in the downstroke and upstrokes with respect to the image process. Okay, now I'm going to move on with the image processing steps, which I have been followed after completing my experiment in the high-speed camera. So this is my flowchart of the steps which I have followed using my image processing. The first initial important thing is the soap bubble experiment video, which we have took from the high-speed camera. So which is like we need to have a particular frame rate and the lighting stream, which are very important. So after recording this high-speed camera video, we will be having a selective area of the region, which are considerably said as the coordinates. We no need to do the entire Matlab processing for the entire frame, because we can only find the vertex simulated over here. So we need to perfectly select the region of interest where the Matlab image processing should be done. And we have to use this same concept for n number of frames. In the next step, you can able to see this is frame 1 to n. There will be n number of frames, because we are going to convert the raw data of my video to the number of frames. So I can able to do the image processing for each individual frames. So as we know, the image processing is a very important method performs the operation of the images to the external information from to enhance. It's the digital image processing has a broad range of applications such as image restoration, medical imaging, and remote sensing and image segmentation. In every process requires a different techniques. So we have also used a kind of techniques. The first important thing is selection the frames and coordinates here, and laterly the color. Laterally we had some reference color thickness where we can compare the RGB images. So based on the reference, we can be able to select the boundary limits, especially in the spectrum colors. So then we will be finding the color, the closest color matching for each pixel using a mean square error. In the coming next slides, I'll be explaining about the mean square error clearly. And later we able to change the color boundary limits based on the lighting setup. The lighting effect will be placing the how good we can able to enhance the video. and assigning each pixel with a corresponding wavelength, because each pixel will having a corresponding wavelength which will be matching to the reference setup. And finally, we will be getting the storage wavelength matrix of each nth frame. Yes, now I'm moving on to the image processing steps done in the Matlab. So first we need to initially take the Matlab interface for the simulating codes. We need to create a new Matlab interface for post-processing of high-speed videos. And then we need to import the high-speed camera video to the number of frames. Here I have imported my video into the Matlab and I have converted to each single frame, where in my total where duration of my high-speed camera is 25 seconds, which totally I have converted my frames is 519 frames. Then we need to start the post-processing each and individual frames with the color enhancement. After the color enhancement, we need to do the color enhancement. After the color enhancement, we need to mostly focus on the thing is that the reference thickness matrix. The thickness matrix we have checked with the size thickness matrix, which we should not be cross more than 600 cross 800, which is the exact resolution of my high-speed camera. So this high-speed camera resolution and as well as the image post-processing of my image should be matching, because this is a very high defined matrix which cannot be opened in the Matlab. We are like customizing that to 800 cross 600, where we can able to get the final data. So after using the final post-processing thickness matrix values with the respective codes, we have finally got the final thickness matrix for each frame. So here you can able to see this thickness matrix is for the respective frame number 322 at the downstroke. So this is how we are going to get the raw numerical values entirely. So once for one single processing of a frame, it approximately takes 20 to 25 minutes in the workstation, which we have around like 700 frames after processing my Matlab video, which can around like take 2 weeks just for post-processing the Matlab data. In later slides, I'm going to explain why we need to do the post-processing for all 700 frames, why we are not taking the interval frames, why we need to do the entire frame processing from frame number 1 to frame number 700. So the computational complexities we are facing when you are doing the post-process simulation is the first thing is about the soft film video consists around like 279 frames in my present case of hovering, and the resolution which I have taken from each frame is 800 cross 600, and the number 621 number is the operations which I need to perform to find the wavelength of each matrix. This number 625 is a particular one pixel of my frame. This is the pixel size for which have one individual pixel. The wavelength of each pixel corresponding to the standard colors chart of my soap film, which we have taken as a reference. So now moving on to the raw data, what we have acquired from the Matlab post-processing after the respective frames we have done. So we will be having the Matlab raw data without doing any noise filtering, which I'll be going to explain there. The final raw data in the Matlab post-processing without any noise reduction. Why we use the term noise is because the wing in the flapping inside the soap bubble will be having some kind of ripples, which I have mentioned in which I showed you in the video. We have ripples which is disturbing our signal whenever we are processing the data, which will be disturbing the process. So that's what we are calling them as the noise ripples, because we know that soap bubble surface is not a rigid one. So considering that as noise, we are doing the low pass filter like the cutoff frequency, which I am going to mention in the next coming slides. So here, starting with the Matlab cutoff frequency, low pass filter and noise reduction. The low pass, what is the low pass filter? The low pass filter produces a slow changes in the output values to make it easier to see the trend about the boost and overall the signal to noise ratio with a minimum signal of degradation. We can also use the Matlab to design the finite impulse response, which is known as FIR, and based on the infinite impulse response IIR based on filters. So we have taken one of the common filter. The two common low pass filters is I have done the low pass filter. As I mentioned, as I need to reduce the noise created while the flapping wing can be done, we can be able to identify the number of ripples. How many number of ripples has been happened in the video multiplied with the flapping frequency. What is my flapping frequency when it is in the test condition? We can able to get the flapping frequency. And but even after the cutoff frequency, we have some slight data mismatch. You can able to see there still the data is not matching slightly because it's uppercase and our raw data is not matching with the after the cutoff frequency. But it is only have some slight mismatch because of the ripples that we can able to visible only on the video. So we can able to do this trial and error method after we are getting the cutoff. We will be getting a standard cutoff frequency using the formula. Even later, we need to do some trial and error methods between the cutoff frequency value obtained from the calculation. So I have started doing my cutoff frequency from 35, 40 and later on moved with 45 and 50. And when it comes to the final cutoff frequency at 50, there is a slight comparison between my raw data and my signal processor data. There is a slight match. So after doing a slight trial and error method to find the cutoff frequency, in our case, it is 50 Hertz. So we have taken the total 4 flapping cycles for the post processing. So you can able to see from a starting point to the ending point, we have used 4 flapping cycles with complete upstrokes and downstrokes, which have been segregated with respect to number of flapping cycles, which I'm going to show in the final processing data. So here I have mentioned my raw data, where the grayscale you can able to see this is my raw data, and the color which is cycle 1 and the color green is cycle 2, cycle 3 and cycle 4, which I have represented here with one upstroke and downstroke, which represents a cycle, and one more upstroke and downstroke, which represent the second cycle of my flapping wing. So this is the total flapping process data after the cutoff frequency. Now we have mentioned the previous slide, the separation of 4 different flapping cycles comparing the original thing. So now I have to mention the 4 cycles up and down with the stroke angles images with representing in the flapping cycles. Now to finalize the validating of soap film data, we have a few options. Among one of them is the wind tunnel data. Because the raw data what I have got from the soap film, I need to compare this raw data with some present existing techniques of the flow pattern techniques. So then only I can finally prove that my data is valid. So now moving on with my wind tunnel data process. So here now you can able to see similarly the flapping cycle 1, 2, 4. But now the data comparison is with my original wind tunnel data, which I have done in my wind tunnel with of 0.5 voltage, which is the input voltage. As we can able to see here, the comparison of the original wind tunnel data with the soap bubble data after reduction of my noise. The main important point while comparing the data is that both the patterns should be like input voltage and the flapping with the wind speed, where in the case of in my case, the driving voltage is only 0.5 volt, because if you are increasing more voltage, the frequency increases, which can tends to breakage of my soap bubble. So we have taken a very low frequency where we can capture my data, and has been hovering case, especially in the hovering case where there is no wind speed. The wind speed has assumed as 0 meter per second. In the furthermore, because this is only a one single wind tunnel data which I have been compared, but still I want to compare my data with some existing technology which is like PIV data, the particle velocity meter process data, which I have taken the reference. In furthermore data comparison, I'm going to show only with the hovering concept motion, which is done within the next slides. So this slide is the this slide I have compromised it from the slide 2. I have only selected 2 slides. I mean 2 flapping cycles here, and I have compared this data. This hovering vertical force data is from the this is a data from Professor Chan from NCKU, who has performed the aerodynamics of an emulated hovering passive with a different wing folding amplitude, where this test this tested data of Professor Chan is by using the PIV techniques. So the professor has used the PIV technique, so which I am comparing my soap film data with the PIV techniques, which is very feasible data to compare, especially in the hovering condition. So this the data professor has done is also the vertical motion, and my data is also in the hovering in vertical direction motion. So where we can able to slightly see the phase 1, phase 2 and phase 3 and phase 4, the same similar like 4 cycles, where you can able to see the 2 peaks which is of thrust. The similarly my cycle 4 which is having 2 peaks with my which is matching with my soap film data. So now moving on to the values displaying. So as I mentioned in the previous slides, I have done with different motions like free stream direction and starboard direction and hovering direction. In the final data we have concluded is that the starboard direction in the wind tunnel test when we have done, the highest is the lift we have got is 1.7 to 1.8 gram force when we have used 1.2 meter per second as my wind speed. But the same data when we have tested in the soap bubble, we got only 0.8 gram force when my flapping frequency is only 7.58 Hertz with the traveling speed of 0.15 because the bubble breaking point. This is the most important key role. And next one is the free stream direction where we got 2.4 gram force with the inlet velocity is 1.2 meter per second. And the same experimental done with my soap bubble in the free stream direction is 3.6 gram force at 20.8 Hertz with the traveling speed of 1.16 meter per second. And in the final, my hovering condition, which we got from the wind tunnel data, is around like 4 gram force per second, where it is in hovering case, no wind speed. So we have mentioned it is 0 meter per second. And the same experimental result we have got from the soap film is 2.8 gram force with 25.8 Hertz as my flapping frequency with 0 meter per second because of the hovering condition. Yes. Now finally concluding with this. So we have finally recorded the unsteady flow using a long lasting soap bubble with my 4th generation experimental setup with the patterns of inverted Carmel vortex, wingtip vortex will be both successfully observed. And in the theoretical formulation about the relation with the thickness matrix and also the color matrix of the soap film has been done for evaluating the jet speed of the downward speed, and it is useful to calculate the thrust and the lift of my MAV. The soap bubble visualization is the work that can emergently output for the quantitative results. After filtering the noise deduced by my free surface wave propagation, which is like the ripples, which we consider as the ripples on the soap film during the flapping, the thrust and the lift waveforms come from the soap film image and the thickness field likely to the wind tunnel data. However, the soap film, the time average net thrust value still deviate from the measured result of my wind tunnel testing very much. The main reason is that the soap bubble ripple noise. Also, the second case is the difference between the wind speeds. The wind speed which I have given is 0 meter per second versus 0.15. So due to the change in the different wind speeds, there is a slight change of the data matching. And next, globally, the soap film visualization is a very low cost method without any dangerous consumers to study the unsteady flow of my MAVs, and it can also be options of a flow visualization techniques beside the smoke tracking and the PIV. And in my future work, we are going to say to increase my soap bubble solution durability because we want to capture more number of cycles to do the more data validation. So the right now the hovering concept what we have done is only for 6 minutes flapping. We are getting the total duration of my bubble. But in future, if we increase the bubble ratio with a different mixing ratio, we can able to get more flapping data to do a greater validation. We can able to test the different flapping mechanisms in future which can be under testing which can be able to identify the wing rotation mechanism to find the flow pattern. Right now we have used only few kinds of mechanisms. In future we can able to also use different other mechanisms with my soap bubble to find the exact flow matters. And we also want to compare the testing results of my soap film lift value with the flow sensor testing results, because of the most flexible parameters is that soap bubble flapping frequency is very less comparing to the original data. So which we can able to measure with the low flapping frequency with the flow sensors. In the present case, both the flow sensor and the pressure sensor designs are under testing process for the data comparison of my lift and thrust. So we can also be able to compare our soap bubble data with the simulation results without any noise rate. Right now we are using a noise reduction technique using a Matlab. In future generations we can able to also use the simulation process to identify the lift and thrust values, so which can be able to help to validate the data. Yes. And these are the some of my journal papers and the conference papers which I have been published within guidance of my Professor Yang. The first one is about the soap film visualization, which we have published in the Fluid Journal, and the conferences and the simultaneous work. Apart from soap film, we are also working on the flow sensors. So these are the few conference papers which I work with my seniors. And this is one of my conference paper, which is in ISME 2020-22. And at this moment, I would greatly acknowledge, I would like to convey my heartful appreciation and gratitudes to my Professor L.J. Yang and his wife, Mr. Yang, and will be my supervisors for providing me with a chance to work on this interesting research work, which is also aided to my condition extensive study, learning about the bunch of few topics of like flapping wing, flow visualization using the image processing techniques. I'm quite grateful to them. The secondly, I want to thank all my lab members, especially Ms. Reshmi Wycombe and Mr. Vivek Jabra Joseph and Mr. Vivek and Mr. Nitish and Mr. Ken and also Mr. Abhishek for their assistance in completing all the project in a very such short period of time. It was a quite useful term to expand my knowledge and the ability, and a special thanks to all my brothers and sisters from my church, those who make me more strong in my spiritual prayers. Yes. Yes, Professor. So now we can move to the questioning section.
Oh, yes. And thanks, Mr. Chandrasekhar. Your presentation is very clear, and I think you have done a good research work. Okay.
Thank you.
And now let us now is the Q&A times. And Professor Wu, do you have any recommendation about the Chandrasekhar's thesis?
Professor, your mic is muted. Professor Wu.
Microphone.
Microphone.
Thanks, Professor Hu. Okay. Chandu, huh? Your experiment is complex and difficult to finish, but you have done in your thesis, I think you should do some revise about the thesis format. For example, you can see the contents. Please notice align the corresponding subtitles. You must align the corresponding subtitle.
Okay,
and,
Prof.
Please see the list of figure. You can find your caption is not well aligned.
Okay.
Please revise.
Sure, Professor, definitely. I will revise all my thesis once again.
Okay. Usually, please see the page 5. Page 5. You can find the figure and your text. There is enough space between figure and your text. So please do some modification to make the figure and the text with more space.
Sure, Professor. Definitely, I'll modify all those corrections.
And please see the page 6. I find many figures you didn't place the your figure in the center of the page. So please correct the figure location.
Sure, Professor, definitely.
Page 8, you can find the figure also shift to the right.
Okay.
Okay. These are about the thesis format. You can do some revise to make your thesis better. In page 28, I think this word may be wrong. I think in the figure caption, I think light box arrangement. I think should be arrangement, not arrangement.
Okay.
Right?
I'll check it, Professor. Yes, Professor.
Arrangement. And in this thesis, I find most of the physical quantities I think in based on ISO standard, I think you should revise your physical quantity format, make one space between number and dimension.
Oh, okay, Professor.
Okay. In page 33, you can see the equation 3.1. I think this equation is wrong.
Okay.
I think the equation should equal to 2 mu d cosine theta.
Yes, Professor.
Multiplied 2 pi over wavelength,
Yes.
right? And I have a question about the figure 3.6. I have a question. In your experiment, you used transparent or reflective type interference. Which one?
Regarding the 3 points in this, professor, we have used the reflective one.
Reflective one.
Yes.
Okay. So do you think the figure in the figure 3.16 do you think this right?
Yes, professor. Up to my knowledge, like when I referred to the few papers, it has been mentioned the same. So if not, I will once again cross check with that figure 3.6, which is matching with the figure number 3.16. And once again, I'll cross check the equation, professor.
My suggestion, this is a 3-element configuration. Yes. So I think in your experiment, you use N1, N2, and yes. N1, yes. 3-element, right? Yes, professor. Because so maybe this figure must should be corrected.
Okay, professor, I will change it.
And I suggest you cite a reference for equation 3.1.
Sure, professor, I will cite the paper.
And in page 35, I think you you can see the second line below section 3.3.
Okay, professor.
You can find for non-constant flow.
Yes.
I think this word maybe changed into unsteady, maybe more proper.
Okay, professor, sure, I will change the words to the unsteady flow.
Okay, and you can find the kinematic viscosity.
Yes.
You can find the symbol mu in page 35.
Yes, professor.
Because the symbol of mu you used in page 33.
Okay.
So these two symbol, for you are different, right?
Yes, professor.
So you must have the other symbol for the kinematic viscosity.
Okay. Sure, professor.
Okay. What is in page 36? What is white force equation?
White force equation.
White force equation.
Yes, Professor, which is deriving from the equation 3.6, which I have taken the reference.
Again, please.
Yes, I have taken the reference from equation 3.1. So I can able to do my two-dimensional image processing in the Matlab to check what is the exact coordinates I can able to give for my the color enhancement.
Mm-hmm. In page 39, I think the format for your equations, my suggestion is make your equation with the same format.
Okay, Professor.
The same problem in page 42, you used a symbol T for thrust, right? But in page 33, 33, you use a symbol T for phase difference, right?
Yes, Professor.
Delta T.
Yes, it is with respect to change in time.
I think these two location you use two similar symbol. This may this is easy to make readers confused.
Oh, sorry, Professor. I will make all the changes.
Page 44. Page 44. The line the oh no the at the last four line. You can find your sentence stand for a few seconds and wait for blah blah blah. But I think this there is syntax error for the sentence.
Okay, Professor, I'll check them.
Okay. See the conclusion. I have a question about your work. Do you think real time envision
Yes.
is possible for your work?
You mean my soap film in the real time?
Real time measurement. No, I think in real time envision. Do you think real time envision is possible for your work?
Yes, Professor, it is a real time possible because we have done the Matlab processing is a technique what we have taken, But if you're using some other technique, something like a simulation process or data comparison with the Matlab, there is an very high accurate chances where we can able to do in the real time case.
And it is the real time envision is useful in your research field? Do
Yes,
you think?
It is a very most important, yes, Professor, it's an important question, and it is very useful, especially in the ornithopter fields, because every ornithopter what we are designing is in the scale of 10 centimeter to 25 centimeters. So when we are having a very less wingspan, the techniques what is like PAV and drum other techniques are very expensive and very hard to evaluate the data. But when we are using the same soap film method, it will be very easy and also the cost constraint. It is very low cost and feasible for the every researcher. They can able to find the lift and thrust values from this experiment.
Okay. Another question. How did you decide your cutoff frequency in your research?
Oh, yes, Professor. Cutoff frequency. Yes, here. As I mentioned in the previous videos of my flapping wing, the soap bubble is not a standard one. So it has some ripples, which is like a kind of wavy form when my MAV is moving. So those ripples will make some like noise reduction. So I will just count n number of ripples happen in the video, which multiplied with my flapping frequency on the soap bubble. So when I multiply with this equation, I will get not an accurate, we will be getting a standby cutoff frequency. But still, as I mentioned in this slide, we need to do some kind of trial and error method to have an exact accurate match. So in this slide, you can able to see there is no match of the data. But when I have done for the accurate 50 Hertz as of my cutoff frequency, there is an comparatively matching with my raw data with my processor data. So we need to do a kind of trial and error method after we derived our cutoff frequency.
Thank you. This is my questions.
Okay. Yeah, thank you so much for your questions, Professor.
Okay, thank you, Professor Wu. Okay, I have a minor suggestion about the abstract. Okay, and maybe if there are any quantitative results, I suggest you can add some key quantitative results in the abstract.
Okay, Professor.
And then, yes, I have a question about the recipe of the bubble liquid. Yes, in your thesis, the table 2.1 lists the recipe of the bubble liquid. And yes. I wonder, is there a optimization recipe to be suitable for all kind of your soap film experiment, or the recipe is dependent on, for example, on the withstand frequency, or
yes, Professor. So the first thing is we need to make sure about the standard frequency, Professor, because if there is a high flapping frequency, as you can see in my videos, the sudden break of my bubble. So if you want to increase the thickness, so we need to make sure to increase more glycerin content, because the density of glycerin is more high. But if you are adding more quantity of the glycerin, the color, whatever the colors you can able to find here will be getting less. So then we need to simultaneously increase the image processing color thickness matrix. So that is a possible way we can able to make a standard mixing solution for all the MAVs.
Oh, okay, I understand. Yeah. And then, another question is about, let me see. Okay, and because I'm not an expert in the field of aerodynamics, and so I'm not sure is the ground force is a common unit in the aerodynamics?
It's not a common unit, professor, but we can able to convert the gram for it's a grams. Just we are adding in the terminology, we can say it is a gram force because grams is an unit like a Newton force.
Yeah, yes,
So we can also just say gram force. So that is the grams. 4 is the grams. We are getting the lift as my value.
Yeah, yes, that's okay. If in the field of aerodynamics, the ground force is a common unit. That's okay. Yeah, because my opinion is we are usually to use the Newton as the
Yes,
force unit. Yeah. Okay.
Yes.
And I find that both the lift or the thrust forces in your soft film experiment
Yes,
are all lower than the force given by the wind tuner test.
Right. Yes, professor.
To understand, yeah.
Yes.
And I guess if the surface tension of the bubble film may draw back the lift or the thrust force of the flapping wing.
Yes, professor. And also the main problem is about the testing wind speed in the wind tunnel is 1.2. But when we are coming to the soap film experiment, it is only 0.15, which is like a half of the wind speed. So when we are matching both the wind speed in my wind tunnel and the soap film, then they will be an accurate match. But as the soap bubble is a breaking point, we can't able to increase more speed.
Okay. And according to my understanding of your thesis, the lift and the thrust force in the soap film experiment are calculated by the equation 11 and equation 13. Am I right?
Yes, professor.
And the values of the force for the wind tuner test, how to get the force? Is there any sensors in the wind tuner test, or also calculated from other formulas?
Yes, professor. Actually, in the wind tunnel, we are using the 6-axis force gauge of a load cell. It is an experiment where we can directly get the lift and thrust values. Okay,
understand. So the force is given in the wind tuner test is the standard values of the force.
Yes,
for the lift and the thrust force. Yes. And in your calculation of the lift and the thrust force using the equation 11 and 13. Yes, in that equations, is there the equation 11 and 13 have considered the maybe the surface tension influence?
Yes, the surface tension we have taken as an H0, which is the thickness of my soap bubble. So that will plays a very vital role where you can able to see this Hij. So this is my thickness of my soap bubble. So this will make a more important replica with the lift and thrust values.
Oh, okay. Yes, yeah. This question is about I try to give you some clues to explain the deviation between the wind tuner test and the soap film experiment. For you. Maybe you can consider the compensation of your experiment results. Okay.
Sure, definitely I'll consider all these points.
Yes. And in the page 60 of your thesis, again, because I'm not the expert in the aerodynamics, and you the cutoff force and the cutoff frequency is equal to the number of ripples
by the flapping
and the flapping frequency. Yes.
Yep.
Yeah. Why we have to multiply the number of ripples?
Because yes, Professor, let me show you the video. So from this video, you can able to see some wave propagation is going to happen with within the flow of my flapping wing. So that waveform will create some noise. So that's what we need to count how many ripples it has been happened, which will be multiplied with my flapping frequency. So we will get some exact frequency where I can reduce my noise.
Okay. Understand. Yeah, thank you. Yes, I have no other questions, and really, I really think you have done a great research work. Especially the soft film experiment design is very sophisticated. Yes.
Yes, Ross.
Yeah. And okay, and Professor Yang, yeah, your advisor. Do you have any other comments? Professor Yang.
Okay. Yeah. Okay. Thank you for the comment from the Professor Professor Wu and Professor Hu. Sorry for my weakness to my body, so I cannot concentrate very much. Due to my COVID infection. Sorry. But anyway, I think Chandu he followed me as he was a UG student. He exchanged to Tamkang. Yeah, when he was a UG student in Beltech, and exchanged to Tamkang. And actually, from that time on, he interested about the flapping wing research very much. And he also want to continue to study the PhD program in our department.
Good,
yeah.
Good, yeah.
So I think he can he can try to extend his research work about the flapping wing continuously. Yeah. So actually, in his work, you can see he tried to summarize his senior's work because the software flow visualization techniques I had developed for almost 10 years. But in the past 8 years, we have no mathematical model. We have no mathematical model to describe why the soft film, what the color and what the soft film, how can he generate lift force or thrust force? In the past, we can only observe the flow features qualitatively, but not quantitatively. It means that we want to convert the color field into a real value, the lift force or thrust force. In our first 8 years experience, almost impossible. But 1 year ago, 1 to 2 years ago, we start to study the mathematical model, and we try to conclude how it is possible to transform into. Actually, you can see how Chandu he tried to combine. This video is done by his senior, not by him. This video is done by his senior. It's the first work. And the flow feature very clear. But this flow feature, Chandu, you can show to the mathematical model about this.
This one, Professor.
Yeah, he includes when we study the model, we see it was composed with lift force and the thrust force together.
Yes.
Lift force and the thrust force couple in this flow field, mixed together. So we cannot separate that. We only have one equation, but we have no two unknown.
Yes.
Where equation it is?
Yeah, Prof. In this equation of the starboard direction, both the thrust and the lift has been integrated together.
Okay, so you can see the equation 6. Equation 6. You can see there is a vertical. V is a jet, right? Horizontal jet. W.
Speed.
No, left hand side. In the left hand side, you can see Z star V bar plus Y star W bar. Y is the downwash. V is the horizontal jet. They combine together and they be equal to the right hand side. Right hand side actually is the total summation of the soft film thickness, right? And take the time derivative. This total term. So this right hand side is come from our soft film experiment. But the left hand side, there are two unknown. One is V, one is W. So we cannot solve the V and the W. So we need another condition, another experiment. So what experiment? So here's another senior do the penetration experiment. Let the flapping wing penetrate the soft film. Try to break it. Okay. So you can see in this experiment, he can let the flapping wing penetrate the soft film and leave gradually. Actually, it's go away far away, not coming up. Actually, it's just go far away. So in this mode, we can use another equation, try to solve the downwash velocity. So we can solve the downwash velocity in terms the equation 10. So it means that we combine his two seniors' work together, so we can solve the W and the T. I mean the W actually is what is the downwash. Downwash can be translated into the lift force. So we can solve the lift force, and then we substitute back to the previous case. So we can solve the thrust force at the same time. But the problem right now is what? So in theoretical manner, it is possible to solve if we can provide very good experiment data, both in the parallel mode and the penetration mode. Then we can solve the lift force and the thrust force at the same time.
Yes,
but the problem is these two experiments cannot be done at the same time. It cannot be done at the same time. So it is the resource of our error. So it's the reason why finally when we summarize the force comparison, you can see sometimes bigger, sometimes smaller, and change the error very big.
Yes.
The error very big. It's because we cannot let these two kinds of soft field experiment to be identical. Very difficult to be identical. Sometimes the flow, maybe your travel speed is different. Sometimes your flapping frequency is not the same, and so on. And maybe your soft film quality also change.
Yes.
Your soft film quality also change. So many factors will change the total quality of your experiment.
Yes.
And one very important thing is the velocity, the travel velocity. For this case, the travel velocity should be very small. Yes. How small it is, Chandu?
It is 0.15 meter per second, Professor.
Yeah, you mean that only 1 second, only 15 centimeter. So it travel very slow. If you travel very fast, soft film broken.
Broke. Yes.
Broke. But in this travel mode, you can see the velocity very high. How high?
It is around like 1.12 meter per second.
Yeah, can be up to 1 meter per second. Yeah, so travel is for the travel mode, the soft film very robust, can sustain for a longer time and a very large flapping frequency. So, but it's also the problem. So it means that we only can confine our soft film experiment in a low speed, region.
Yes.
So in Chandu's work, actually he doing the work about the hovering. Hovering can solve this problem because hovering is almost no speed. It's just hovering in the air.
Same position.
Yeah, it's the same position. So we don't need to try to make our flapping wing moving. So we can try to we can study the case of the hovering. So he tried to redo the soft film experiment, but try to let the flapping wing right now under the situation of hovering. So he tried to study about this question, and hovering also the problem right now. Many people have interest in about that. Hovering is more interesting than forward flight for many researchers. Of course, there are some printing the room can be improved about the experiment, and also scissors, many detail about the scissors format or wording. Chandu, you need to try to correct. Chandu, you need to try to correct many things. How to align, how to make it the format very beautiful. It's your duty. You need to try to revise this from the first page to the end. Yeah,
definitely, Professor. I'll take all the comments as good suggestions, and I will change all the things, and I will update you, Professor.
Okay, so I try to explain his work. Actually, he summarized his senior's works very much, and I'm so delighted. This was also published in a paper in Fluid. Fluid is a good journal. It's a very new journal, but I'm very happy this work can be accepted over there. But anyway, Chandu, would you please spend 2 minutes to say your feeling about this research or your future work? Yeah, 2 minutes. Yeah.
Yes, Professor, sure. Especially when I started doing this experiment, I have started reading my senior's paper, and I just want to know what is the trouble they have faced. When the troubleshoots they have faced is only with the solution mixing. The mixing solution they have made is around like 7:1:1, which they can able to get only the 2 minutes of the breaking point. So I just want to figure it out. If I increase the soap bubble mixture time, I can get more flapping cycles. So that is how my initiation has been started. So then I started mixing with different kinds of solutions and came up with an best mixing ratio, which is 2:4, which can able to come up to 2 minutes 14 seconds of the bubble log. So within this 6 minutes of my bubble lasting time, so I can able to adjust all different kinds of angles, either both in free stream direction, starboard direction, as well as hovering condition, to get more flapping cycles, especially for the data analysis. Because in my previous seniors things, they have also the data, but they have done with an minute intervals of change, which facing with some extraction of the exact data. But now I have taken with each and every point for the data processing, which got a very good results and which can be accepted in the paper very furthermore. And in the next future, I'm also going to test, especially with the flow sensors and the pressure sensors, because the PIV techniques and the internal techniques, which are very expensive and very hard to do the experimental setups. So, but if right now in our lab, we are also doing some kinds of flow sensors and pressure sensors testing going on. If I use those sensors to validate my soap film data, it will be very feasible, especially because my soap bubble, the flapping frequency is very low because of the soap bubble. So that's low frequency flapping data will not be exactly comparable with an high flapping frequency wind tunnel data. If I use my flow sensor or the pressure sensor, which I'm doing in a very low flapping frequency, then there is a high chance of mixing with my comparing with my soap film data. So that is what I'm going to do in my next future work. And as well as I also want to do some kind of simulation works where I can reduce the image processing techniques. Yes, Professor.
Okay. Yeah. So yeah, that's it. So the Professor Hu and Professor Wu, if there is no question, maybe we can discuss. Can discard his score. 看看如果没有问题，我们是不是再评分一下这样子？ Okay. So Chandu, please leave for a while. We want to discuss.
Professor. Okay, bro. Actually, after that, we need to take a group photo.
Oh, take group photo. Okay.
Okay, Professor. So can you please
take the group photo?
Yes. Just a minute, Professor. Professor, can you just please turn on your camera?
Who?
Professor.
I have turned on.
Okay, Professor. Just a minute. Okay. Yes, Professor. Professor Yang, we can't able to see your.
队长，你的头像没有出来。
对啊，我明明我摄影机是开的呢。
你可能要重新出去再进来。我以前遇过。
哦，这样子。对，我一直没看到，没看到杨老师的脸。
好，那 wait a minute, I leave and enter once again.
Okay, Professor. Okay, you want to say? If you want, okay. Professors, okay, just we are waiting for the Professor Yang. Once if he enters, we can able to.
有了。
Yes. Yes, Professor. Okay, Professor, just a minute.
Okay.
Is it done?
So it's done.
Yeah, yes, done. Yes, done, Professor. And okay. Professor, Reshmi sister wants to say something, so.
Please, anything?
Yeah.
Oh.
Reduce the speaker.
So
yeah.
What's up, Reshmi?
Good afternoon, professors. I'm PhD student of Professor Yang. I have been doing my research for 4 years under Professor Yang guidance. And Chandu, I just want to say a few words for Chandu because he is my junior. He is very obedient and diligent, my junior. He not only did his soft film experiment, he also helped me in doing my experiments. My research work was more related to the design of CMOS flow sensor, and I also needed some help from my juniors, like during the test in the wind tunnel. Chandu used to increase or decrease the wind tunnel speed, or sometimes testing my flow sensor into the flapping wing. So Chandu overall helped me a lot. Yeah, and I wish him all the best for his further PhD studies under Professor Yang. And Professor Yang is a very good guide. if we follow his words and if we continue doing research under the guidance of Professor Yang, we can gain a lot of new knowledge in future. Yeah, thank you everyone.
Thank you so much, Reshmi.
Okay. Yes, Chandu, you can leave. You can leave temporarily.